All right, now we're going to look at limits and continuity of functions of several variables. And first off, well, it's we're going to define a function in the interior of a circle with center AB. Okay, except it doesn't have to be defined at the center. So it's defined in the interior, but maybe not at the center. And the definition of limit as xy approaches AB means for every epsilon greater than 0, there exists a delta greater than 0 such that if your x and your y are inside the circle, a radius delta, then your function's close to L. And I can draw a picture of this. So here's our domain, and here's our center of a circle, AB, and F is defined inside the circle, so we have, let's say, here's a point X, Y, and it's going to go to Fxy, but that's going to be close to L inside L plus epsilon and L minus epsilon, where the radius of the circle is delta. So if we take any point in there and get closer and closer to AB, then the F of xy is going to get closer and closer to L. And in other words, for every point xy, except possibly the center, doesn't have to be defined at the center, inside the circle with radius delta, the number corresponding to f of xy is in the interval L minus epsilon, L plus epsilon. Now the same rules apply as with regular functions of one variable. Suppose let's look at a polynomial. And polynomials are continuous if they have in one variable. Well, it's the same for two or more variables. Where you can just substitute in and get a number, the limit. And that's true because it's a polynomial. And polynomials are continuous. I know we haven't defined continuity, but it's the same for functions of more variables. Now let's do an epsilon delta proof. We want to prove that the limit of 2x plus y equal 4 as xy approaches the point 1, 2. Okay, so two things. Number one, the function is defined, because it's a polynomial, in the circle around the point 1, 2. And what we need to show is for every epsilon, there's a delta. such that when you're in that circle, then f is close to 4. So we're going to use a triangle inequality to do this. And for our scratch work, because it's going to show us how to go, we're going to start with f minus L. And we're going to use a little trick. We're going to subtract 2 and subtract 2. That's going to give us our minus 4. And using the triangle inequality, that's less than 2x minus 1 plus y minus 2. And both x minus 1 and absolute value y minus 2 is less than or equal to that square root. Because with the square root, you're adding an extra positive term. This isn't a positive term right here. Like for the x minus 1, the square root, if you just look at this part of it, the square root of x minus 1 squared is the absolute value of x minus 1. But you're adding something to it, so that's going to make it larger. You're adding the square term, which is positive. That's going to make it larger. Okay, so we have the square root less than delta, so then 2x minus 1 plus y minus 2 well, let me put all the steps in. So that implies x minus 1 is less than delta and y minus 2 is less than delta because both of those are less than the square root. So then 2x minus 1 plus y minus 2 is less than 2 delta plus delta, which is 3 delta. So let's choose epsilon to be 3 delta, or delta is epsilon over 3. There's our key. So that's going to help us work frontwards. We're done with our scratch work. So we want to show for every epsilon, if since 0 is less than x minus squared plus y minus 2 squared, that's the circle with radius 1, 2 is less than delta, then two x minus 1 plus y minus 2 is less than 3 delta, which is 3 times epsilon over 3, which is epsilon. And so that, remember where we got that, that means that 2x plus y minus 4 is less than epsilon. Because that's less than by the triangle inequality. And we proved what we needed to prove. Okay, let's look at some specific examples. All right, if we take the limit of this as xy approaches 0, 0, we cannot evaluate it because we get 0 over 0. So let's take it one at a time. Let's just let x go to 0 and keep y constant. So we're along points on the x-axis. These are points along the x-axis. And before I do that, I need to make a point. Just like with regular one variable functions, if the function, this is a really important point, has different limits as xy approaches AB through two distinct sets, then the limit doesn't exist. It has to have a unique limit. TNE does not exist. Okay, so we're going to look at this. The first set of points we're going to look at are on the x-axis and let x go to 0. So if we let y be 0, we have x squared over x squared, which is 1. If we do the points on the y-axis, let x be 0, then it's negative 1. And these are different, so the limit does not exist. No matter how you approach it, it has to be the same limit. Look at another one. Let's go along the x-axis. So we let y be 0, and that's 0. Let's do on the y-axis. Well, so that looks like it's the same, but that doesn't prove anything. To prove it, you have to use the epsilon delta to prove that the limit exists, because you could do this all day long. There's an infinite ways that it can approach 0, 0. But if you find two ways and they're not the same, then you can stop. You find a counterexample. But to prove what the limit actually is, you actually have to do the epsilon delta proof. All right, let's go along the line y equal x. So where x equals y, we have x squared on top. We have 2x squared on the bottom. That's a half. So these aren't the same, so the limit doesn't exist. So we found another pathway where it's approaching a different point. So that's the usual approach to these problems is to find two pathways where the limit isn't the same. And the definition of continuous is the same for function of one variable. Continuous at a point if the limit xy approaches AB exists, if the point exists, at AB, and if the limit's equal to the point. Okay, so you have to have these three conditions to be continuous. And it's continuous on a set if it's continuous at every point in that set. So that's important too. So that definition that I wrote down is continuous at a point. If you want it continuous at a set, then you have to show that it's continuous at every point in that set. And everything we talked about is the same for a function of 3 variables or more, and they can all be extended.